we can. Okay, let's go.
Okay, so yeah, thanks for the introduction. I'll talk to you a bit about the research that I do in Eindhoven on pulse-based optimization of variational quantum algorithms. And as already said, we do our research in the city of Eindhoven. So you see a picture of our campus. You see a picture of our city center with, of course, the Philips sign there. So that is the company that basically built our beautiful town. And then, as you can see, it's not that far away. It's only 5.5 hours by bike, which is our standard measure in the Netherlands. So we also have this football club, which I briefly discussed with Frank yesterday, but we don't talk about that. So a little bit about my background. I studied both mathematics and physics in Eindhoven, my master's and my bachelor's there. And the work that I did for my master thesis, which mostly encompasses this all, I did in collaboration with Sebastian Hockemans, who's here now from physics, and Oliver Say from the mathematics department. So a bit about the big picture of our project, what we do in Eindhoven. I'm part of the CAT1 project, which is the Catalyzer 1 project, which we do in close collaboration with the UVA, University of Amsterdam. And the main idea is that we build a Rydberg platform for quantum computing. So we use these neutral atoms as our qubits, and we want to build this demonstrator with around 10 to 100 qubits and run hybrid algorithms on it. And the idea is that within the span of 4 years, we can build this system, hook it up to this online platform, Quantum Inspire, so that people all around the world have 24/7 access, and we can send them in. They can send in jobs, and we run it on our system, and we send it back. So we both have an experimental and a theoretical side. So I decided to also introduce the Rydberg system a little bit, because the people I've talked to here often work with superconducting. So since I knew very little about superconducting, I thought maybe it'd be good to introduce Rydberg here. So the idea is that the atoms, the qubits that we use, are a register of strontium atoms, strontium-88, which we then individually trap in laser optical tweezers. And our 0 and 1 levels of our qubits are then energy levels of the strontium atom. So first we use this 1s0, which is the ground state of strontium-88. And we also have this 3p0 state as our 1 state. And these 0-1 states are connected by this 698 nanometer line width transition. And that is called the clock transition. It's a doubly forbidden, very narrow transition, which means that we can drive these qubits very precisely, create very good fidelity gate operations between the 0 and 1 system, and it's very well isolated, which is also the reason why they use this transition in optical clocks, hence the name clock transition. And well, of course, it's very nice. These are very well operated and isolated from each other, but we also need these qubits to interact. And for that, we use the Rydberg level, which is this very high lying energy level where one of the valence electrons in strontium, it has 2, gets excited to a level with a really high principal quantum number n. So that you see here, this 5s ns state, and the size of this atom, so the extent of its radial wave function, increases as n squared, and the van der Waals interaction, which is the interaction that the qubits feel with each other, grows as n to the power 11. So we get this really strong interactions once we're in that level. And it also scales with the interatomic distance to the power 6. So we do this van der Waals interaction. And on the left bottom there, you see a grid of these qubits, which is then trapped in these laser optical tweezers. And that is what we are planning to make and currently making. So the advantages of this Rydberg system is that it's very stable because of the 0-1 transition. It's easily controlled, so we can individually address our qubits by shining individual lasers onto them. And we have a very long-range interaction, namely this van der Waals interaction, which might also allow us to interact with non-neighboring qubits. That's a big advantage. So what I'm going to be talking to you about today is this paper, which is now in preprint, but we've also submitted to Quantum Journal, called Pulse-Based Variational Quantum Optimal Control for Hybrid Quantum Computing. And on the right, you see the most beautiful picture in the paper in there, because of course that's what you have to put on a slide like this. So I always leave this slide in. I guess it's very familiar for you, so I won't say too much about it. But the point that I'm trying to make here is that, you know, the concepts of superposition and entanglement in quantum computing allow us to do very cool things, which you all know, like Grover's search algorithm, the Shor's algorithm, things like secure quantum communication. But we're not quite there yet because the era we're currently in is this NISQ era. So noisy intermediate scale quantum, which is a phrase coined by John Preskill in 2018. And this means that our qubits, of course, the gate operations don't have full fidelity, and we can't scale up to the levels we would need to do things like Shor's algorithm. But we can still do very cool things in this NISQ era. And one of these things, I think the main working horse is variational quantum algorithms, which are based on this concept called the variational principle. Very easy concept, which says that if I apply a wave function to an observable, I'll never get a value which is bigger than its lowest eigenvalue, so the minimal eigenvalue. And if we take an observable like some sort of molecular Hamiltonian, then this equivalates to its ground state energy. But what we can do is we can exploit this by somehow parameterizing our wave function by these parameters theta, and then optimizing this to somehow approximate this ground state. So the goal of a VQA, in the way I phrase it always, is that we have an initial state, psi 0, for instance, just our 0, 0, 0 state on our qubit system. And we want to evolve this in a time capital T to this ground state, which has minimal energy. And we want to do this in a NISQ-friendly manner. So what we have built up are these three criteria. We want our evolution time to be as small as possible, because we still have these decoherence effects, which we can then suppress. We want expressibility of the entire Hilbert space. So we really want to be able to have a very versatile algorithm that can approximate any ground state for any molecular Hamiltonian. And we can start with many different initial states. And we also want easy to implement evolution. And what I mean with that is that we want a very natural way of controlling and evolving the system. Now, the main algorithm for this, so the canonical one, is the variational quantum eigensolver. And the idea behind this is that you take this sequence of quantum gates, which some are parameterized and some are not, and that sequence you call your ansatz. So that is just the way your wave function evolves. And what you then do is you take some initial parameters and you measure its energy. And there's very many different variations of this. But the most basic one, what you really do is you have your parameters, you measure your energy, and then you slightly perturb your parameters, you measure the energy again, and you see if you increase or decrease. And based on that, you either take a step in that perturbation direction or not. So in one iteration, the number of quantum evaluations, so QE here, is about 2 times the number of shots, where the number of shots is the times you repeat the measurement to get some convergence of your expectation values. And then you have this classical algorithm, which then updates the parameters. So in this case, it was just really easily explained as a perturbation, and then you do it back. And you repeat this until you have sufficient convergence. So in all these VQAs, what you'll see is this interplay between quantum space search on the one side, where you prepare your wave function and you evolve it and you measure it. That's what you really do in the quantum system. And then you do classical optimization on it. So that's why it's called hybrid. Now, if we want to see if this is actually, NISQ friendly, if we can do this, we have to look at our criteria. So the first one was that we want our evolution time to be as small as possible. And in an algorithm like VQE, the evolution time is really determined by the gate sequence. So as soon as I have my gate sequence, I basically know exactly how long my algorithm is going to take. And I really can't tweak this in any way. So I can't make it like fractionally smaller unless I update how I implement my gates. And one disadvantage of that is nicely illustrated by this block sphere. So if I have this red state over here, and I want to map it to this state, then in a VQE algorithm, what you would likely do is, for instance, a Z rotation and then a Y rotation. So you take the direction of these green arrows. Well, in principle, your system probably had the level of control that it could immediately evolve via this blue line, the lowest distance, and therefore reach the state much faster and at less decoherence. Secondly, a gate sequence always inhibits the reachable state space that you have. So you can imagine if I do something very dumb, like I only include Z rotations in my gate ansatz, then I can't even reach this state over here. But you know, with every gate sequence, you will never open up your gate space more because you always limit the control that you have. And as a third way, it's not quite trivial how to implement certain quantum gates. So in a theory simulation, you might have figured out, okay, a C0 gate here or a phase gate might do very well here, but then you have to find a very complex sequence of laser pulses to actually implement this gate. So it's not as natural. And the question that we asked ourselves in Eindhoven is, can we do better? And to do that, we really have to take a step back. So we have to look at our initial goal again of this VQA, which is that we want to evolve this state in time t to this ground state. And as with every other quantum system, this evolution is governed by the Schrödinger equation, which you see here in propagator formalism. I hope you're all familiar with that. But the propagator U is just a unitary that describes how your initial state evolves. So we can do it for any initial state. But that is the equation we want to solve. And really what now is our goal in this VQA is to create this time-dependent Hamiltonian, which then evolves our initial states to the ground state in this evolution time t. What is important in that are two ingredients, our Hamiltonian and our evolution time. For that, we have something called the important concept there is the quantum speed limit, which I illustrate with these images here. So here in red, you see your entire Hilbert space of qubit states. And then in orange, you have all the states you could reach under a certain Hamiltonian that you have implemented. So if you have a certain shape of your Hamiltonian, you can reach a certain subset of all of your states, as long as you had enough time to actually evolve there. Now, if your evolution time is also limited, so in case we have a very small t, then we have this green area of states we can actually reach within that time. And we need to make sure that the initial state that we have, you know, that will always lie in that space, no matter how small our t is. But the state that we want to reach, we also have to have in this green space. So we need to make our evolution time t big enough to actually include this final state in it as well. And that is what's called the quantum speed limit. So that kind of determines how fast your system can evolve from one state to another. But if we choose our t very large, what will happen is during an optimization process, you might find a very suboptimal path. So you will take very long to actually reach this space or the state where you could have done it much faster. Now, the Hamiltonian here is also very important because that determines this orange space. So you can imagine if, for instance, my Hamiltonian doesn't have any interaction terms, then I can't have my qubits entangled, and all my entangled states will lie in this red space over here. So I also need to make sure that my Hamiltonian is somehow exotic enough so that my ground state also is, we can approximate it through this evolution under the Schrödinger equation. So in our project, our Hamiltonians will mostly take this shape where we have this drift Hamiltonian that is fixed and a control Hamiltonian that we can actually control by sending pulses to it. So that has these pulses Z and these operators QL. And by adding more terms QL to this, so having as much control as possible, we can really open up the search space. So how are things like VQE now made from this approach? So if we take a step back, well, first we have to determine what our system looks like. So we have to look at the Hamiltonians that describe our qubit system. Then we have to determine what level of control we have on that. So for instance, if we have our 0 and 1 levels and we want to drive that transition, we do that with a laser, which has a certain coupling strength, which has a certain detuning. And those are the things we or experimentalists actually control. And what you normally do then is you figure out certain pulses, either with something also optimal control like, or with thinking what these pulses actually do, and you figure out how to make certain gates. So you might have for your system described a certain pulse that creates this X gate. What you do is you parameterize these gates, you parameterize certain aspects of your pulses, and then you have this gate-based optimization. But our idea is that really you can see all these pulses of all these gates, you can concatenate them and then see them as one big pulse. So basically you're just sending one big parameterized pulse to your system, and that is what he calls your qubits. So what you can do is you can just skip these steps and immediately optimize for these pulses. So that is then pulse-based optimization in a VQA sense. And that brings me to the main body. So this was mostly background, but I promise it won't take like as long as you would expect here now. But I first want to talk to you about these pulses on a Rydberg system. So the system that we actually have in Eindhoven, what do we control? How do we describe this, model this? Then how do we actually optimize this? So this is the algorithm that we've developed and described for this pulse-based approach of optimal control, variational quantum optimal control. And then I'll just illustrate it to you and also compare it to this established method of VQE. So here you see a nice illustration which kind of juxtaposes the two. So on the one hand, you have this gate-based approach, on the other hand, you have this pulse-based approach of evolution. And just to look at if we can get NIST-friendly, well, first of all, we have this evolution time criterion. And what we can, of course, do is we can just say our pulse has to be this long. So if we want to make it fractionally smaller, we just set our evolution time lower. And the only thing we really need to make sure is that our evolution time is now bigger than this quantum speed limit. Whereas gate implementations just have this fixed time. Then we can also explore the Hilbert space more because we don't limit ourselves in how much control we have of the system. If we just take all the control parameters we have, like laser intensity, the tuning, certain magnetic fields, then we just have all the control. We could never ask for more. And it's also a more natural implementation. So instead of having these predefined pulses, which you really don't know where they come from, in case like optimal control, then here we actually know what these do on an experimental sense. One caveat here is that, of course, it's no longer really intuitive what happens to your qubits. So you know that if you do an X rotation, so if you're X gate, you're rotating it on the block sphere, a C0 operation, you know, okay, these are the qubits that are now entangled. And that is something you give up when you go to the pulse-based approach. But I think in general, you can say that in the NISC era, this is a more approachable method than gate-based operations. So on a Rydberg system, we're going to zoom into this part, how we actually determine our Hamiltonians. And as I already said, we basically split our Hamiltonian up in this drift Hamiltonian, which is something that is always present and we don't control, and this control Hamiltonian. So in drift Hamiltonian, what we use is basically this passive always on interaction, which is the van der Waals interaction. And in this case, we assume that our one state is also our Rydberg state, just for computational complexity. And that is the drift Hamiltonian we choose. So if you have more control in your system, for instance, if you can control these C6 coefficients between atoms, or you can do something else by having like very local magnetic fields that changes this interaction, you might be able to create other drift Hamiltonians. And in this other paper that we wrote 2 years ago, we actually find that this is very influential in your convergence. So if we were able to implement other drift Hamiltonians, this can be very useful as well. And then we have our control Hamiltonian. And what we really do is we take these laser parameters like coupling strength and phase of the laser and the tuning, and we all encode them as complex numbers, just as a more general sense. Most of these are, of course, real, but I'll show you why we use complex numbers later. And then what we do is we always take this shape of our control Hamiltonian. So we have a sum over all the controls. We have capital L number of controls. Then these ZLs really are our pulses that we use, and these QLs are the operators that describe what happens physically. So in a Rydberg system, this is just a system that we use, two-level system. We drive this transition between these 0 and 1 levels, and the 0 and 1 levels have a natural frequency. Our laser has a frequency, and the difference between that is called the tuning. So that is the thing we control. And we have the coupling strength, this omega, and that is basically, you can see that as the intensity of the laser. Now we use these atom light interactions, which you can derive semi-classically, and that then describes the interaction between our laser lights and our atoms. So as you can see here, you have this term, which is the coupling strength and the phase of the laser. And together, that makes one complex number. So that is why we use these complex numbers to describe, in that case, the coupling strength and the phase together. We also have this term here, the tuning, which adds a phase onto the one level physically. And what we do there is we also encode this as a complex number, but now in this case, our QL and QL dagger are the same because this 1-1 operator is Hermitian. And therefore, we can write it in that way as a complex number plus its conjugate. So in total, that then describes a real number. So in many cases, experimentally, you won't have control of your laser phase on the same level of control as the coupling strength and the tuning. So we can do kind of the same trick there where we choose just our QL as the sum and then it becomes Hermitian and then we just describe it as a real number. Now, if we just have something like this, so if we only have this control over the phase and the coupling strength, then we can basically transform any state on the Bloch grid to any other state, and that is why we also call this rotational control. Now, there are proposals in which we can also do something like Rydberg dressing, where we basically mix in some of another Rydberg state to tune our interaction strength, and in that case you would also control the interaction strength, so you get this extra term where you also control this. So that might be another control parameter, but normally that is a global addressing. So what you have then is that these pulses that you have described are all equal for all pairs of qubits as well. So how do we actually optimize this? That is, of course, this part of the scheme. And this slide gets a little mathematical, but I'll try to do my best to explain it a little terms-wise. So here we have this functional, which is dependent on two things, the pulses on the one hand, and the unitaries that we get from these pulses through the Schrödinger equation on the other hand. And this is the thing that we actually try to minimize, and we must be subject to this control equation. So that is, in our case, just our evolution equation, the Schrödinger equation, with the initial condition that our propagator starts as the identity, and our control Hamiltonian looks like this. And what are these terms? Well, we write it in density matrix and propagator form just because this is a more general description. But if your initial state is a pure state, then you can just write this as the energy of your final wave function. So that is the main thing we try to minimize. But what we also have to watch out for is that we don't get any unrealistic pulses. So we don't want to add almost infinite energy to the system to actually reach these states. So we also punish for the norm of these pulses, which kind of keeps them bounded a bit. And what we now do is we have to define the space of pulses we actually minimize over, and that is the space of controls. So that is all the controls we can choose from, all the pulses that we have. And we make sure they are in this L2 space so that we can actually describe them with such a norm. And we also have the extra condition that the infinity norm remains bounded. So what that means is that at no point in time can we actually exceed a certain norm. And this also makes sure that even over a small time period, we don't add too much energy into the system. And mathematically, for this system of interest, what we have proven is well-posedness of the Schrödinger equation. So we know that if we have pulses within this space, then we always get a well-defined mathematical solution. And we've also proven existence of global minimizers. So we know that within this space, there are certain unique pulses that actually minimize this functional. So this problem has solutions. Now, how do we actually solve it? That might be a little bit more interesting approach. So what we do is we actually use this Lagrangian optimization where we add this Lagrangian term as our constraint. So we have this Lagrange parameter, which is called the adjoint once you start to look into these Hilbert spaces, which is eta, and that lives in the same space as our propagator u. And what we now do is we maximize over these etas so that we know if this term here isn't equal to 0, then maximizing over eta would basically make this functional infinite, and then we can't minimize later on anymore. So what this really does is it really restricts the system that it always sets this to 0 if we want to minimize something. And then what we do is we calculate the derivatives with respect to u, z, and eta, and we set all of these derivatives to 0, and then that gives us certain conditions for minimality. And we then use some iterative scheme to actually update these pulses. So what you see here is the pulses at step k plus 1 are equal to the pulses you had before that, plus some gradient step, where alpha is your step size. This lambda times z comes from the fact that you punish for the size of the pulses. So that was the second term here. And this first term here is really the gradient with respect to the energy. So that is the thing the most interesting thing. And that is what we can actually calculate efficiently on our quantum computer. So we have certain expressions for what this adjoint operator, this eta, should look like, and we can all write this out and then find out that we can actually calculate these things efficiently using things like Hadamard tests. So if we have good enough control on our quantum computer, we can calculate what these gradients have to be and then find out what our updates of our pulses should be. So if we actually want to implement this, we discretize our pulses. So we take this stepwise approach to the pulses, and then the number of quantum evaluations which we have to do per iteration, that does grow quite drastically when you compare it to VQE. So we have to have, we have 2, which is just 3 factor, times the number of time steps that we do. So that comes from this discretization. We have the number of controls we have to check. So for instance, if we have coupling, strength, detuning, and entanglement, that would become 3. Or if we have it for a lot of qubits, then this becomes of the order of the amount of qubits that we have. And we have this other decomposition factor, which you get from these QL operators, and that is for these Hadamard tests. And what we often find is that this is 2 or 4. So it doesn't really matter what this is, it's just a small number. I don't know why this suddenly happened on my screen. You just didn't see that. But yeah, now I just wanted to illustrate the system. And the problem that I'm trying to solve here is a 4-qubit problem. It's the molecular Hamiltonian of lithium hydrogen. And we look at a system where we have an interaction strength between our qubits of 0.1 kilohertz, which is kind of for a rubidium or strontium setup, a realistic parameter. We have this van der Waals drift Hamiltonian, so that is just a natural interaction. And we only assume rotational control. So we assume control over the coupling strength and the phasor or laser. And we let this run for about, the evolution time is 100 milliseconds. And what I did is I got all these molecular Hamiltonians for the different interatomic distances. And then I calculated their exact minimal energy, which is this full CI approach. The Hartree-Fock energy, which is some benchmark in quantum chemistry. And then the energy we get from quantum optimal control. And you see that, especially at the end, it is nicely approximate to the full CI method instead of this benchmark HF energy. And here you see the errors in the log scale. You see that in very many cases, it is able to converge to quite low errors comparative to what VQE would do. If we zoom into one case here at 0.9 angstrom, you actually see that only after 12 iterations, so very fast in the number of iterations, you get below this Hartree-Fock energy and the chemical accuracy, which is another benchmark in quantum chemistry, which is the energy where you start to be able to realistically predict what certain reactions would do. And here you see the optimized pulses. So here you see the real part and the imaginary part from which you could reconstruct the phase and the coupling strength of these lasers. And you see that they are nicely smooth pulses that you could implement on your system. Their strength is about a kilohertz again, and that is a realistic thing you could do on a laser system like we have. Now, here you actually see the evolution of what would happen to your qubits. So on the right is the ground state that you want to approximate of one of these lithium hydrogen molecules. And on the left, you have your initial state. And these are the pulses that come out of the algorithm. So those are the things you implement. And if you have that system run, then it just optimizes like this. And eventually, at the end, you'll start to see that this state on the left nicely approximates the state on the right. If we do that for the lithium hydrogen molecule, so the one you just saw was for some random 3-qubit Hamiltonian. This is a 4-qubit Hamiltonian lithium hydrogen. That's a little bit more boring to see, as the ground state is quite boring here. But what you see is that you really drive this initial state, so all the weight you have on that, you drive it to this ground state over here. These are just the density matrices description you see here. So now we get to maybe the most interesting part is how does this actually compare to already established algorithms like this VQE? And for that, we have to look at a few things. So let me just get all these slides here. And two things are very important. So first, we have to define a measure on how we actually say these algorithms, how we compare them. So we could do it via iterations, but that really isn't fair. So what I propose is that we actually compare them on the number of quantum evaluations done on your system, as that basically translates to the strain on your quantum computer, which is probably your limiting factor in this NISQ era. So we know that per iteration, we do 2 times this K times L, which is the number of controls, and N, this discretization step evaluations for QOC, and 2 for VQE. So that is our measure of how good this is. So we compare the energy error we get as a function of the number of quantum evaluations. But we also need to make sure that evolution is sort of comparable. So what we use in VQE is what's called the hardware efficient ansatz, which is a very well known and often used one, where we have this these Z-X-Z gates, and what these Z gates, they're all parameterized, so they rotate around the Z axis, then the X, then Z again. And that allows us to map any state on the block sphere to any other state for the right parameters. So basically that is rotational control as we have it in VQOC. And then we also have an entanglement operator. And what we do is we just take the matrix exponential of this drift Hamiltonian. And what that means physically is we just have the system sit there for a certain time. And what we find is that the Z-X-Z rotations we can do within 1 millisecond, because we have almost 1 kilohertz of Brabus frequency. And then we just let the system entangle itself for this 10 milliseconds. And we do that d times, which is the depth of your ansatz, which means that in total, the time it takes to run this circuit would be t times, or 11 times this depth. Now for VQE, we do the same. So we take our evolution time to be exactly the same as this d times 11. And we have this rotational control. So we control the phase and the coupling strength. And we just have the drift Hamiltonian the same as we include there. So there you really see that the evolution in both cases are quite comparable. And in all simulations, you'll now see we have this rotational control, drift Hamiltonian like that, and this interaction strength. And we choose our discretization step to be 100. So this capital M equal to 100. And there's 3 problems that I want to show the results of. So we have this lithium hydrogen molecule, 4 qubits, and that is a minimally entangled ground state. And we look at that for medium depth, which means in this case depth 5. Then we do the same for a highly entangled ground state, this H4 molecule. And then we also look at very low depth ansatzes, also for this H4 molecule. What you see are the following results. So here you have the lithium hydrogen. We start off with a Hartree-Fock as our initial state. And what you see is that both algorithms get, of course, below this Hartree-Fock state, and they compare very similarly. So after 3.2 times 10 to the power 4 quantum evaluations, you see that VQE and QOC reach similar levels of energy error. But it gets interesting if you actually zoom into what happens at different distances. So in all the cases we looked at for this medium depth or high depth systems, what we see is that quantum optimal control does very well for low interatomic distances. So on the left here, you see that quantum optimal control gets an energy level which is low way faster. In this high interatomic distance regime, you actually see that VQE does better, but quantum optimal control hasn't fully converged yet as well. And in the middle, you start to see that these get eerily similar in convergence. And this is quite weird because VQE is a stochastic method, whereas in quantum optimal control, we actually have these analytic gradients. And the one is pulse-based and the one is gate-based. So it's very weird to see that these convergences are quite the same. And we also see that with this H4 molecule, where we get very similar energy errors, but in this low interatomic distance regime, quantum optical control is much better. High interatomic distance regime, VQE is better. And in the middle, we have this same behavior again. So we are still looking into why this is actually the case, but one of the things we think plays an important role is that at these high interatomic distances, the ground state of these molecules is way less entangled than this low interatomic distance regime. And apparently VQE kind of is able to handle these lowly entangled states much better, whereas quantum optimal control is able to get to these highly entangled states much better. Now, the last interesting case is this highly entangled ground state for H4, but we only look at really low depth. So we take one level of depth, so 1 times a ZXZ rotation and an entanglement operation for VQE, and that translates to 11 milliseconds of evolution time for quantum optimal control. And here what you really see is that quantum optimal control is able to get below this Hartree Fock energy level, but VQE really isn't able to do much better than that after this 4.8 times 10 to the 4 quantum evaluations. And this is just an illustrative case, which you basically see everywhere, that VQE just gets stuck in this local minimum, whereas variational quantum optimal control apparently has enough speed to beat this quantum speed limit and really evolve more towards the ground state than this VQE can do. So what are our conclusions here? Well, as I already said, I think this is quite clear. VQE performs better at low interatomic distances, VQE better at high interatomic distances, and VQAC performs better at very low depths / evolution time. And this is, I think, the most interesting in the NISQ era, because there the evolution time and all the decoherence effects are way more important. So yeah, there the VQAC really shines. So I think the conclusion is that, well, this variational quantum optimal control is a more natural algorithm in this NISQ era, and it's able to compete with these established algorithms like VQA or VQE. And yeah, up next for this project, we have submitted this currently to Quantum Journal, where it is under review. We also are looking into more implementation challenges. So this was mostly my master's work, and in my PhD work, I'm really looking at this system to theory approach, where we really start to look at what can our system do, what are its limitations, what pulses can it implement, what can't it, and then translate this in theory to an algorithm that can handle these challenges. So for instance, a Rieberg state only has limited lifetime, so we can't excite that too much. We have to think about things like readouts. So how do we ensure that our state stays stable enough for our time to actually read it out? We are also looking into these barren plateaus. So we have results which show that also with this optimization algorithm, we reach these barren plateaus. You can actually prove that pretty much. And yeah, we also want to look into these mitigation of errors. For instance, if we include motional states in our problem, how do we, yeah, can we still optimize over them? So here's a little bit of what I'm doing now, very short. So we've kind of increased our time-dependent Hamiltonian, and the basic things is that we now look at a 3-level system. So we have our computational space 0, 1, but we also have that Rieberg level, which I showed in the previous slide. We have 2 transitions between them, both with coupling strength and the tuning again. But now we also have these photon recoil terms, which basically, if a transition happens, this qubit absorbs a photon and also absorbs its momentum, which might interact with its motional state, and that might excite the system to a state you don't know about. So that is something we have to take into account. And we also include the different traps, so the trapping potentials that they feel because of this optical tweezers, that also plays a role in these motional states. We have our interaction Hamiltonian the same again, and we also have this decay rate, which now models the limited lifetime of this Rieberg state, and that is modeled, this Hamiltonian, we mostly, this model we have from this paper, error budgeting, and we're just trying to see if we can still implement these QOC, these natural algorithms for systems like this. So that was my presentation with this. Thank you for the invitation.
Thank Thank you. So now we have to deal with local and delocalized questions. So maybe we start with local, and then Anurag can moderate the chat. Anurag, you still hear us, I assume?
Yes.
Okay, very good. So are the questions in the room? Yes,
I have some. So, okay, so the first question is maybe I missed it in the talk, but how do you come up with an ansatz in this kind of, let's say, an initialization ansatz in
You mean the initialization as you choose your initial state, or
your
the
initial,
control?
maybe your initial parameters, because let's say you talk about this issue of variable plateaus, which I see why it would emerge also in this case. And so let's say you would like to somehow have an ansatz so that you end up in a region with non-zero gradient ideally. So how would you do that?
Yeah, so I think for that you really have to look. It is a topic we've discussed as well, and it of course depends on the problem you're looking at. So these molecular Hamiltonians, if you look like, you have very simple atoms like lithium, hydrogen, where okay, likely some of the lower lying shells of lithium will be populated. So there you can already say, if I want to be close to my solution, I'll start off with some qubit stage which already describes this. And if you look at more complex molecules, this in some sense gets a little easier, where likely you can point out areas where electrons will, or certain orbitals will already be occupied. So there you can, if you could somehow make that translation step to what qubit state that encompasses, then you have a good initial guess for a state to approach there. I think the other thing you have to look at is how do my controls indeed translate to the evolution in the qubit space. So you have to make this translation between, on one side, the controls, and with things like these atom-light interactions, that's really easy because okay, my coupling strength is the thing that determines if I can go from 0 to 1. And the tuning is something that adds phase and somehow blocks this transition. So if you're able to know what these parameters do to your qubit evolution, what control over these parameters gives you, it also shows you what space or how well you can explore this Hilbert space. So if okay, I need to make sure that I excite into these electron orbitals and these, then you might also choose your initial state based on, okay, this is what I have to reach given these certain controls.
Yeah, I would say it really depends also on some quantum chemistry knowledge of the molecule you're studying. I mean, as how the chemists do is that you always come up with an ansatz. You say, okay, I have these orbitals and I make this position, or like a product state, this position of these, and this is how I start, and this is like my long-range solution. And here you actually do the same, and you just transform it to a qubit Hamiltonian. But essentially, it's the same ansatz. That's what you would do. Let's say with another quantum chemistry.
So in VQE, you have these problem-based ansatzes, where, for instance, for these quantum chemistry problems, to say, okay, we take this coupled cluster ansatz, which somehow includes the excitation operators to these electron orbitals, and that is then more natural for that problem, and they do get faster convergence with these type of things. So if we can develop some sort of same problem ansatz, maybe by saying, okay, this is then the sort of pulse shape you have to take, because I think that is the analogy in these pulse-based algorithms, then that might lead to better results.
Yes, another question. In general, do you have an estimate of what the quantum speed limit is? Can you actually get it? You just know, okay, the quantum speed limit is this. I don't know how to get there, but is there a way to estimate?
Yeah, there are. I think that is something that is a very hot topic of research right now, where they look at this geometry, these spaces of 1 qubit, you get the block sphere, 2 qubits, you have some other it's like 7-dimensional block sphere type of thing. And what people are trying to do is really develop good distance measures on that. So one of these things is this quantum Fisher information, and that is a thing that mostly determines this quantum speed limit. So there are ways of calculating this right now, but I still think it's, yeah, to bound it indeed. It's hard to fully calculate, and often these bounds are quite rough. So to actually calculate, I think would require a very high understanding of these Lie algebras. And I don't see that feasible yet for these systems, but you can imagine if someone has a really smart idea about that, we can maybe get some better estimates.
Okay. More questions in the room? I have one.
Yeah.
So I would assume that usually you need to constrain your optimal control, because otherwise you could, if you do Jordan-Wigner, you could accidentally put too many electrons into your molecule.
Mm-hmm.
So first of all, do you have to do this, and are you constraining or are you penalizing?
I think if you want to stay in this Jordan-Wigner has this nice reduction, right? Where you can already.
In those cases, we want to, ideally, we want to make sure that the reachable states are the ones that are actually physically allowed. And, we have to deal with the fact that not everything is physically allowed in a molecule.
Yeah, I think what you would have in these VQE algorithms is either you take off one of these qubits or you ensure that your gates somehow let you stay in a state where, for instance, the electron number is.
How do you do this optimal control? Because constraining is typically hard, so you resort to penalties.
I think constraining would even kind of harm the convergence, because it wouldn't matter if you take a detour through a space which has, the wrong electron, which describes states with the wrong electron number, as long as you end up back with the right electron number. So you could add a penalty term that kind of, you measure your state, you see, okay, this is the number of electrons it describes, and you penalize for that. And very similar, what we research now is if we have these three states, then what's going to happen is you have your 0, 1 R state, but you know that your solution lies in this 0, 1 space. So at the end of your pulse, it might happen that your state has reached this Rydberg state. Somehow it's in there. And what we do to avoid that is just penalize that at the end. But we really do want our states to take this tour into the Rydberg states before the evolution is ended, right? Because that is the only place where it can actually entangle. So what we see there is that we really have to go through these spaces to reach our solution. And I think similarly, it's actually an advantage of pulse-based that you could go into these spaces that describe the wrong electron number, as long as you are able to come back.
There are more questions in the room.
We have some questions
online.
online.
Questions online. Yes.
Yes. So first, Simone.
Hi. Thanks for a nice talk. Just a very simple question. I mean, when you explain what you have been doing for optimizing your pulses, I wanted to ask you, what is the relation with the grape algorithm? It seems that was it, but you didn't mention that, so maybe you are doing something differently.
Yeah, so it is quite similar in that in the problem descriptions and the way these gradients are calculated, but we really start from this adjoint approach. So with this Lagrangian optimization, which I think grape somehow, sort of skips. So in the derivations I've not seen these as solution methods, but they are very similar in how they.
And it's what is called Krotov, right?
Yeah.
Okay. So that's Krotov algorithm, essentially, what you.
No. So in grape they use this Krotov, and we use this adjoint approach where you get these gradients analytically, but then you have to discretize your pulses, and then they don't become fully analytic anymore. So I think there is a difference in where you start to make your approximations of these algorithms. So also with grape, what you don't see is, for instance, these well-posedness results and these existence results, which you can get from sticking with this adjoint approach for a little while.
Okay. And then another very quick question is, you, for example, when in your result you said that you were taking 10 time steps to discretize your time evolution, or 100, sorry, time steps. I mean, is that enough? Have you checked convergence?
Yeah, so what we see from some simulations is that we do get enough from this. If we were to implement this experimentally, then I think a first approach would just be to have very little of these time steps. So, you know, you have this very simple waveforms, which are the stepwise functions, which you would then implement. If you really scale that up, then you require more control from your system. So you require these pulses to be implemented very precisely on smaller time scales, but you also really scale up the demand on your qubit system. So you have to evaluate these gradients at every point at this time. And if your pulses are just, you know, in your eyes then smooth, then there really isn't too much use in scaling this up anymore.
I mean, trotter error of your simulations are taken into account or not?
Yeah. So they will make an error there indeed. Yeah, I haven't calculated what it would be like analytically. So that might be an interesting thing to do where we have some analytic expression for what the evolution would look like without any discretization, and then indeed see if this trotterization induces error in the state we reach. So we can kind of calculate some fidelity measure for that then. I think that would be a good thing to look into as well.
I mean, my question is that if your simulation is you know reproduces what would happen in your hardware, and that's only true if your trotter error are small enough. Yeah.
So that is of course true, and then yeah, we would have to analyze what these trotter errors are. On the other hand, is the fact that these variational algorithms are always able to correct for what I call coherent mistakes. So what you will often see, and that is also a thing that they research here with these C3 projects, is that your simulation process will have somewhat different parameters from your experimental setup. But as long as these experimental setups are also consistent in the parameters that they have, for instance, these differences between the energy levels of the atom, or they use slightly different trapping frequencies, as long as this is consistent, then this variational algorithms can correct for it. So they just look at this evolution, and based on those evolution results, they can then calculate what the gradient is. So if this is the same for all iterations, then it can inherently correct for this. So you don't need the full theoretical the same behavior in your simulations as you would have in an experiment.
Thank you.
Okay, we have a question from Malay. If he is still online, otherwise, okay, he is.
Yes, so you mentioned that you can show that you reach barren plateaus. Here, show means numerically, or can you prove that analytically?
Yeah, so I have some slides about that later on, which I have to cut. All the way in the end, I think. Yeah, so for this algorithm, we've proven that if we sort of discretize, you can prove that your unitaries you get at every single time. So either the unitary in front of the operation that you use at that time or afterwards becomes a two design. If you assume you have some universality properties for your system, which likely you have because you have some entanglement operator and you have full rotational control. And then you can prove that the gradients of your energy respect to these stepwise parameters in your control functions, that these gradients become exponentially or have an exponential probability of becoming reasonably big. This is a result we have proven, but we have not published in this paper as well, because we decided to leave Blatter out of it. And numerically, you also see that as your number of qubits increases, so this goes from 3 qubits to 7 qubits, you see that the averages of these gradients fluctuate around 0, and their variation drops well, exponentially in this log scale.
Okay, and this result from McLean, I believe you have now proven an analog for this for quantum optimal control, but it's not published. Okay, but this result from McLean proves that the hardware efficient design, especially the layer by layer structure, that looks that starts to become a 2 design. So it's could it be possible that if you had let's say particle conserving unitaries, you would do better in terms of barren plateaus?
Yeah, so this is really proven for this very general control Hamiltonians, where you just have these bounded, not even Hermitian QL operators, and then these pulses living in these L2 spaces. Then you can prove this, but of course it's, you average over all of the control you have via these Haar measures and these universality reasons. So if you have more, I don't know, problem-inspired controls or very special controls where you only sample from a certain subset of all the unitaries you can get, then this result might not be valid anymore. So indeed, yeah, similarly to VQE with different ansatzes, you can imagine that different pulse shapes or different controls wouldn't lead to barren plateaus.
Thank you, Robert. If I may, if I have a minute, I would also like to ask the rest of the Jülich community if they're aware of some software tools to benchmark barren plateaus in, or just study optimal control landscapes. That would be helpful if you could post it on the chat.
Okay. While we wait for the answer to that in the chat, we have one last question from Fila. I think that will be the last online question, and maybe you can continue the discussion in person. Fila, are you still online? Otherwise, I'll read out your question.
Yes, I'm here.
Okay,
can you hear me?
Yes.
Wonderful. All right. Thank you for the presentation, Robert. I really liked the part on the quantum speed limit. I thought that was a very nice representation. I have one major question and then maybe a small one if there's time. So you have made the comparison of the hardware efficient ansatz to VQOC. And in a recent discussion, I understood that this is quite a general ansatz, and there's often more efficient ones, which are more tailored to this particular system that is being looked at. So I was wondering if you've looked at other VQE ansatzes as well.
Yeah, so that's something we haven't really looked into too much yet. I think it would be interesting to look at. So if we propose, for instance, some master's projects which would look into things like this. I have tried certain things where you change your shapes of your pulses. You might say, okay, the only thing, we don't have these stepwise approaches, but we use linear combinations of Gaussians or sinusoidal functions, which then would translate to sort of a different ansatz. But what we really indeed have to do is then find a way, if we have this certain VQE ansatz, how do we make the pulse-based analogy to that? So yeah, what we're first trying to do now is really get these type of things working for an actual experimental setup as we're building in Eindhoven. But it would definitely be a thing we could do in the future to look at these different ansatzes, which are more tailor-made for certain problems.
Okay, and concerning the optimization itself, you were showing that you're using a gradient descent method with this alpha.
Yeah.
So is there a particular reason why you are not using something like LBFGSB or something similar that is usually known to be a little bit more efficient?
Yeah, so we were we have just code that can actually implement things like LBF, LGF.
It's fine, no worries. We all know what's meant.
But you could in principle do that. We thought it would be interesting to actually look at a full analytic result. So if you look at all of these minimizations, for instance, all the way back here. Yeah, I think these show it. Then you really see monotone convergence. So you always go down in energy. And we thought it'd be interesting to really steer away more from this VQE algorithm, where we both look at gate-based versus pulse-based, but also stochastic versus analytic. And the thing we are looking at now with this with a bachelor student that has recently started is to also look at this parameter-based VQE, which was introduced by Maria Schultz, which actually uses these Hadamard test type algorithms to determine analytical gradients per parameter for things like VQE. And if we've implemented that, then we can actually see what makes the biggest difference here, right? So is it the analytic versus stochastic gradients, or is it the pulse-based versus gate-based things? And we could also then implement indeed another optimization method, for instance, LFGS.
Yeah, no worries.
And then we really have the entire 2x2 grid of algorithms filled, right? And then we can really see what makes the biggest difference here.
I also noticed that in these things you were showing here, the initial guess for the pulse-based optimal control is significantly better than the one for the VQE algorithm.
Yeah.
Have you tested comparing with similar initial guesses to see whether that is one of the reasons why the pulse-based one converges better, faster?
Yeah, so I think this image is a little might be a little skewed, because I think the first data point is actually left out here at 0. But what we really do is we start off with all 0 pulses and all 0 parameters in this VQE. And what that means is that the initial evolution really only happens because of this drift Hamiltonian over your evolution time. And one small difference in that is still, if you look at this image over here, is that in the VQOC time, you would do your drift for 11 times d, so that is then the time you evolve your or the time where the drift Hamiltonian is active. Whereas in VQE, if you take all your parameters to be equal to 0, so you don't rotate at all, you just do 10 times d this drift. So that is really the only difference in the initial initial evolutions. But yeah, I can imagine indeed when you don't see it as much on this right image or on this middle image, but on the left, it really seems like QOC starts off better, but that is just because the first step is really so good. You can kind of see that in the second step, that is really the step that takes it down a lot.
Might be good to kind of, even if it doesn't fit into the graph, to prolong the line to go to that point. Yeah. No, nice. Thank you very much.
Okay, so then I would say we at least wrap up the online discussion here.